Leo has been working on this cardboard drawbridge all afternoon, but the moment he tries to assemble the final pieces, the entire structure collapses. Looking closely, we can see exactly why. The main roof piece is completely lopsided, and the curved drawbridge is cut too short to reach the opposite wall. We pull out rulers to measure things all the time, so it feels like a simple task. But getting a measurement exactly right requires a specific set of rules and techniques. When parts fail to fit together, it usually happens because the builder is fighting against the physical shape of the object itself, or falling victim to a common optical illusion. To build a stable structure, we have to match the correct measuring tool to the object's geometry and look at our measurements from the perfect angle. Let's start with the drawbridge. Leo is trying to find the circumference of a round cardboard tube by holding a stiff plastic ruler across its surface. This diagram shows the problem. A straight, rigid edge cannot wrap around a curved surface, making accurate readings impossible. We fix this with a flexible measuring tape. It bends to sit perfectly flush against the curve, and those gaps disappear. Straight rulers are the correct choice for flat, linear surfaces. You would use one to check the length of a flat desk or a straight piece of wood. But three-dimensional curves require flexible tapes. Think of a tailor taking your waist measurement for a shirt, or a botanist checking the trunk size of a growing tree. The physical geometry of the object has to dictate the flexibility of your tool. Forcing a rigid ruler onto a curve immediately introduces errors into your measurements. Next, Leo is cutting the flat roof. He has the right rigid ruler for his flat piece of wood. But notice his posture. His head is leaning far to the side while he reads the numbers. Reading a scale from an angle creates a specific optical mistake called parallax error. Parallax error is the apparent shift in an object's position when you view it from an incorrect angle. In this 3D rendering, viewing the edge from a sharp angle causes the red sightline to intercept the ruler at 15 centimeters. But shifting your perspective directly above the point makes the illusion vanish. Looking straight down, the wood actually ends at 14.5 centimeters. You probably experience this with analog wall clocks. From the side of the room, the hands might look like they're pointing exactly to 3 o'clock, but stand directly in front of the clock and you see it's actually 2:55. Highly accurate tools are useless if the human eye introduces optical distortion. To guarantee precision, a direct top-down viewing angle is essential. There is one final challenge. Leo needs to figure out the length of a winding, squiggly line drawn on a flat map to create a pathway for his model. A rigid ruler won't bend along the path, and a standard measuring tape is too wide and clumsy to accurately trace a tight, irregular squiggle on a flat page. Instead, we can use the string method. You take a piece of flexible thread and carefully lay it directly over the exact path of the curve. There is one critical warning here. You have to follow the curve closely without pulling the thread tight. Stretching the string will create a falsely lengthened measurement. Once the thread covers the entire path, mark the end point with a pen. Then, simply pull it straight against a standard ruler to read the true length of the curve. There is an alternative approach called the divider method. This uses a geometry divider tool, which looks like a compass with two metal points. You open the points to a small fixed width, like exactly 1 centimeter. Place one point at the start and gently walk the tool along the curve. It steps end over end, marking each interval until the finish. Finding the length is simple. Multiply the total steps by the divider's width to reveal the exact length of the entire curve. Measuring irregular curves requires us to adapt. We either translate a complex shape into a straight line using string, or we break it down into small, easily measurable straight segments using a divider. Back in the makerspace, Leo confidently applies these new techniques to his cardboard materials. First, he matches the tool to the shape. He reserves his flexible tapes for the round columns and keeps his rigid ruler for the flat roof edges. Second, he checks his posture. He positions his eyes directly over the measurement marks to defeat parallax error. Finally, he patiently walks a divider along the paper plans to accurately calculate the length of the winding courtyard pathway. Now, his cardboard model fits together flawlessly. The roof is level, the joints hold tight, and the structure is completely stable and proportional. It is easy to picture a great project in your head, but precise measurement is the necessary bridge that takes a good idea from your imagination and turns it into a working creation in the real world.